Yes, good morning, and this is Shivashankar Rajamani from KSR College of Engineering, and we are celebrating our 25th year of academic excellence. Today, I will be taking about optical fiber communication. In that, signal degradation in optical fibers. So, signal degradation here refers to absorption or scattering or bending losses. So, its attenuation will be the main signal degradation in optical fibers. The content of this scattering. So, I will be taking scattering, the overview of scattering, then types of scattering, linear and non-linear scattering. Linear scattering, in that you have two types, one is ray-long scattering, another is Mie scattering. The next type will be your non-linear scattering. In that non-linear scattering, it's stimulated Brillouin scattering, which you call it as SBS, and stimulated Raman scattering, which you call it as SRS. Then comparison of linear and non-linear scatterings. So, we will go to the content. So, overview of this causes of attenuation. Attenuation here refers to the signal degradation during the transmission of the fiber. So, one of the attenuation will be the material absorption. We are not going to discuss about material absorption, and next will be your material scattering. In that, material scattering is again divided into two, one is linear scattering, another is non-linear scattering. It is based on the wavelength, frequency, phase or remains same, then you call it as linear scattering. Your input and output of your wavelength, frequency and phase will be the same, whereas if there is a change in wavelength, frequency or phase, then you call it as non-linear scattering. The phase will be different, that is called as non-linear scattering. This linear scattering is again divided into ray-long scattering and other is Mie scattering. Likewise, for non-linear scattering, it is stimulated Brillouin scattering and stimulated Raman scattering. So, scattering losses occurs when wave interact with particles that removes energy in the directional propagation wave and transfer it to other direction. So, here the wave energy is being transferred from one to another, that is you call it as scattering. There are two main types of scattering, one is linear scattering and another is non-linear scattering. This linear scattering, the amount of light power that is transferred from a wave is proportional to the power in the wave. It is characterized by having no change in frequency in the scattered wave. Linear scattering causes significant power scattered in all directions. Then non-linear scattering, which is accomplished by frequency shift in the scattered light. Non-linear scattering is caused by high values of electric field within the fiber modes to high amount of optical power. Non-linear scattering causes significant power to be scattered in the forward, backward or sideward directions. So, we will deal with linear scattering. Linear scattering is a type of elastic scattering where the scattered wave has the same wavelength, frequency and phase as the incident wave. The energy of moment of scattered wave are considered in linear scattering. Linear scattering can cause the transfer of optical power from one propagating mode to another, resulting in attenuation. Attenuation is the loss of signal during the transmission of our light pulses. Linear scattering is a type of scattering that happens when wave or light will hit an object and that is scattered in different directions. But the scattered wave has the same wavelength, frequency, that is number of waves per second, and the phase position of the wave as the original wave. So, even though if it has been scattered, it will be having same phase, wavelength and phase. Linear scattering losses is categorized into two. One is Rayleigh scattering and Mie scattering. Both the result from non-ideal physical properties of the manufactured fiber, which is difficult in certain cases. So it's impossible to eradicate at present. So they say that Rayleigh scattering will be compulsory in your fibers, and Mie scattering will be very less. We will deal about Rayleigh scattering. Rayleigh scattering is a form of elastic scattering that occurs when light interacts with small particles or objects that are very much smaller than wavelength of incident light, caused by microscopic variation in the refractive index of the fiber core, which occur normally during fiber manufacturing. So this Rayleigh scattering is because of this, if there is a minority variations in the fiber during the fiber manufacturing. This inhomogeneity manifests themselves as refractive index fluctuations and arises from density and compensable variations which are frozen into glass lattice on cooling. So because we are making a fiber that is made up of glass, so sudden cooling will be there. So because of that sudden cooling, there will be a compositional variation in the lattice, glass lattice. Rayleigh scattering is responsible for blue color of the sky and white color of the clouds. The scattering of sunlight by the earth atmosphere causes shorter blue wavelength of light to scatter more than longer red wavelengths, making the sky blue appear. Similarly, clouds appear white because water droplets that make up clouds scatter all directional without same wavelength. Scattering is due to density fluctuations, which is almost in all directions. Procedure for attenuation is directly proportional to 1 by lambda power 4. Here your Rayleigh scattering, which is equal to its 8 pi 3 divided by 3 times lambda power 4 n8 p square beta c k into tf, where mu r is the Rayleigh scattering coefficient and lambda is the optical wavelength and p is the photoelastic coefficient, n is the refractive index of the medium, and beta c is the isothermal compressibility of fictitious temperature, which you call it as Tf, where k is the Boltzmann constant. So it is indirectly proportional to the wavelength, lambda power 4. So Rayleigh scattering spread in all directions, forward, sideward and backward, but only in backward and sideward components contribute to attenuation. Here Rayleigh scattering will be in the range of 800 to 1600 nanometers. So generally we will be using all your light in this range. So this is the Rayleigh scattering, which is dispersing the light in all directions. Then you will see about another type of linear scattering, which is Mie scattering, which is a type of scattering that occurs when light interact with particles or objects that are comparable in size to the wavelength of incident light. So this is very little bit more than Rayleigh scattering. In optical fibers, Mie scattering occurs when light interact with particles or inhomogeneity in fiber core or cladding that are larger than wavelength of incident light. Mie scattering is responsible for modal noise in multimode fibers, which is form of signal degradation that occurs when light propagates through multiple modes in the fiber. So this, because of this Mie scattering, it will generally be more in multimode fibers. The fiber core or cladding can cause light to scatter between modes, leading to variation in optical power distribution among different modes. Linear scattering may also occur in inhomogeneity, which are comparable in size with guided waves, which result in non-perfect cylindrical structure of waveguide and may caused by fiber imperfections, right, irregularity in the core cladding interface. The inhomogeneity can be reduced by removing imperfections due to glass manufacturing process, carefully controlled extrusion and coating of the fiber, increasing fiber guidance by increasing the relative refractive index difference. And this is the me scattering, which will be in the order of lambda power 10, which will be more in the forward direction. And next is your nonlinear scattering, which is elastic scattering that occurs when light interact with particles, which is not proportional to the intensity of light. Here you have wavelength, frequency, and phase will be different. So the energy of momentum in scattered will conserve this. Nonlinear scattering, its most type of nonlinear scattering are Brillouin scattering and Raman scattering. This Brillouin scattering is regulated in thermal molecular vibrations within the fiber, which has the lower side bands, which will cause in both the direction. And this is stimulated Brillouin scattering, and it is energy or quasi particles associated with compression of waves with sound or vibration of the crystal lattice. The frequency shift in maximum in the backward direction, reducing to 0 in forward direction, making stimulated Brillouin scattering, which is mainly drawback process. Here it is given by threshold power, which is directly proportional to the wavelength of square. Then simulated Raman scattering, which the optical intensity which will be inside the glass lattice when the vibrations are associated with optical photons, whereas acoustical photons are associated with Brillouin scattering. When two laser beams with a different wavelength propagates together, Raman scattering will be activated. In addition, lattice vibrations are excited, leading to temperature rise. This Raman gain of longer wavelength beam can be exploited in Raman amplifiers and Raman lasers. Here it is directly proportional to the wavelength. And comparison of linear and non-linear scattering. For linear scattering, the frequency is not changed, whereas in non-linear scattering, frequency shifted. Here it is Rayleigh scattering and me scattering are the types. Here Brillouin and Raman scattering. The linear scattering takes place because of material irregularities, whereas non-linear scattering takes place high optical power interaction with the medium. Linear scattering effect has signal attenuation in most of the cases, whereas non-linear scattering will take place because of crosstalk, power transfer, or backward reflection. So significance, linear scattering will be present in all the fibers, whereas non-linear scattering will be at the high power rate. And thank you. I need your suggestions and feedback, and subscribe to my channel. Thank you.